So I'd like to see if we can continue using this process of the general chain rule to see if we can come up with a more succinct formula for the chain rule for specific cases like exponentials and natural logarithms. So we're going to look at a couple of examples of each of those and see if we can kind of identify a pattern that might be a little bit easier for us to use. So here, in this first example, I have y equals e to the 4x. And I think that when we're working with exponentials, it's going to be a little bit more difficult at first to pick out that inner function just because we don't have the hint of the parentheses. Remember last time I said, hey, parentheses are a really, really big hint as to what your inner function should be. But if you can identify this as something that kind of looks like e to the x or e to the u here in this case, I look at that and I see, well, I want my u to be a function of x. The only function of x I see is that power. So if you can identify this as e, as an exponential function essentially, e to the x or e to the u, every single time when it comes for that first step to identify your u is simply going to be whatever this power is. So u is going to be 4x. Just like last time, we're going to need u prime, so let's find the derivative of that. That is just 4 using our power rule. So okay, we've got step 1 done. Step 2, y equals, I'm going to take out that 4x, I'm going to replace it with u. So I have y equals e to the u power. Step 3, I want to take the derivative. So y prime derivative. So what does the derivative of e to the u look like? Derivative of e to the u, well, I would expect it to act a lot like e to the x, and I know that the derivative of e to the x is e to the x. So the derivative of e to the u, that's just going to be e to the u. So let me just go back real quick to that general chain rule. So essentially what we just found f prime of u. We still need to multiply that by u prime, and that's going to be a common occurrence in every single one of these problems. So I need to multiply this because I've rewritten it. Anytime you make this substitution over here with u, you have to multiply by u prime. So I'm going to multiply this by u prime, and for reasons which I don't really have a good reason other than this is just the way it's written, I'm going to switch these two around and say u prime times e to the u. Usually an exponential just comes last. Step 4 then, we're going to take our u and our u prime and plug those back into our derivative. So y prime is equal to u prime is 4, times e to the u is 4x. So my derivative here is 4e to the 4x power. Can't really simplify that anymore. So hopefully this process feels really similar to what we were doing in the last video. We're just working with a new type of function, but the same 4 steps we're using here. Let's look at part B here. I have y equals 8e to the x squared plus 1 power. Just like last time trying to identify that function of x, the only function of x I have is that power. So I said earlier, I think exponentials can be a little bit more difficult to initially pick out the inside or the inner function, but I think once you identify that's an exponential, it's just the power. Like you don't really even have to think about it. So my u in this case is my power. It's x squared plus 1. Derivative of u prime, that's just 2x. So okay, I've identified my u. Step 2, I'm going to I'm going to rewrite this in terms of u. So y is equal to 8e to the u power. So okay, this is something that I know how to take the derivative of. And remember, that's kind of the goal here, is we end up with something that's a little bit simpler, something that we know how to take the derivative of. so that in step 3 I can take the derivative. So y prime, derivative of 8e to the u, again, it's not going to change. It's 8e to the u times u prime. I'm just going to multiply that by u prime. And just like I did up here in the last example, I'm just going to bump that u prime to the front just because that's how we write it. I don't have a good reason other than because I told you so, essentially. 8 times u prime times e to the u. And I should say, it's not necessarily wrong for you to leave it like this, but for the formula that we'll be using, and just about every formula you'll see for derivative of e to the u, you're going to see it written in this form. So I'm just trying to stick with the conventional way of writing it. So I have my derivative, but it's in terms of u. My last step, I need to take out my u prime and my u and plug in my functions of x. So y prime equals 8 times u prime is 2x, so 8 times 2x times e to the u, that's going to be e to the x squared plus 1 power. And again, if you can simplify this, this is not terribly difficult to simplify since it's two monomials, so we'll just multiply those two together real quick. We have 16x e to the x squared plus 1 power. There is my derivative. So I know we only have two examples here to work with, but I want to see if I can come up with a general formula for specifically e to the x when we're using this chain rule. Let's see if we can identify a pattern here. So after I rewrote this as y equals e to the u, I want to identify, because that's what I have here, e to the u, what does the derivative look like? Well, I rewrote it in this way. I said, hey, you should probably write it as u prime times e to the u. What about this guy right here? I've got 8e to the u, and ignore that 8. That 8's just a constant multiple. Remember, constant multiples don't have a big impact on our derivatives. We just multiply the derivative by that same constant multiple. We just multiply the derivative by 8. So what's the derivative of that e to the u part? That's u prime times e to the u. So if I'm working with y equals g of x, which I can maybe rewrite as y equals e to the u, then the derivative of that function is y prime equals the derivative of my power, which is u prime, times e to the u. So this is the derivative of e to the u using your chain rule. And you can use it on pretty much every exponential function that we'll be looking at. And we'll practice using this formula in the next video. So we've talked about the power rule. We've talked about exponentials e to the x. The other big derivative rule that we've talked about is natural log. So I want to make sure that we address that as well here. So first up, I've got y equals natural log of x cubed minus 2. So again, I'm going to fall back on the same 4 steps we've been using. I'm going to start by identifying u and find u prime. Here we have the parentheses to help us once again, so I'm hoping that picking out u will be a little bit easier. It's going to be x cubed minus 2, so x cubed minus 2. I know I'm going to need u prime, so let's multiply or find our derivative, 3x squared. So okay, I've got u prime. Let's rewrite our function then. So y equals natural log of u. So this is, oops, that was my second step. Again, your goal here is to end up with something that you know how to take the derivative of. Well, I know how to take the derivative of natural log of u. I would expect it to be like the derivative of natural log of x. Derivative of natural log of u, then, that's going to be 1 over u. But remember, anytime you make this substitution with u, we need to multiply by u prime every single time. So I'm going to multiply this by u prime. And just like I did last time, I think it's probably just going to be easiest. We're going to have to make this simplification anyway. I'm going to write that as u prime divided by u. Because if we don't simplify it now, we're going to have to do it later. Might as well do it now. My last step, I've got this derivative that's in terms of u. So I'm going to take my u and my u prime and plug those back in. So rather than u prime over u, my derivative, u prime, that is 3x squared, divided by u, that's x cubed minus 2. There is my derivative. Generally, natural logarithms will not have much, if any, simplifying to do at the end. Let's look at one more just to see if we can't cement the pattern. Here I have y equals 3 times natural log of x squared plus x plus 1. Again, identifying that inside function, u is going to be x squared plus x plus 1. I got to take that whole thing. 2, oops, not 2, excuse me, I need to find u prime. U prime, derivative of x squared plus x plus 1, that's going to be 2x plus 1 using my power rule. So step 2 over here, we're going to make our substitution. Y is equal to 3 times natural log of u. Again, don't get worried about that 3. Remember that 3 is just a constant multiple. All that means is in the next step, we're going to multiply our derivative by 3. So when I go to find y prime, my derivative is going to be 3 times 1 over u times u prime, because I need to multiply by this u prime every single time. And again, I'm just going to rewrite this as 3 times u prime over u so that it's a little bit easier to pick out the pattern in just a second. So I've got my derivative. All that remains is to substitute for u and u prime. So y prime equals 3 times u prime. U prime is 2x plus 1 divided by u, that's x squared plus x plus 1. So we could probably leave it like that. Might be a little bit better if we wrote that as 3 times 2x plus 1 divided by x squared plus x plus 1. Or if you wanted to distribute that 3, we could do that as well. We could say 6x plus 3 divided by x squared plus x plus 1. Here's our derivative. So I want to see if I can generalize if I have natural log of g of x, which I rewrite as natural log of u. So what's the derivative of that look like? Well, here we had natural log of u. We started off with this, with 1 over u times u prime, and I said, you know what, I think this is easier, u prime over u. The next example, I was able to rewrite that as 3 times natural log of u. Again, that 3, that constant multiple, not going to be all that big of a deal. I wouldn't even pay attention to it right here. Because I have that 3 times the derivative of natural log of u. We said that was 1 over u prime, or better yet, u prime over u. So if I want to talk about the derivative of natural log of u, y prime then is just u prime divided by u. If you want to, some textbooks will use 1 over u times u prime. I don't really care. I just think that this version is a little bit easier to work with. It looks a little bit nicer. It looks a little bit more simplified. But that is the derivative of natural log of u using the chain rule. So at this point, we've really talked about the 3 big types of functions that we're going to look at. We talked about essentially polynomials, kind of x to the nth. Talked about exponentials. Talked about logarithms, all with the chain rule. So in the next video, I would like to take a look at some examples where we use these kind of more specific formulas. If you don't like using these specific formulas, if you feel like you've actually kind of gotten pretty good at using this 4-step process, you can continue to use that by all means. But I think that just having this formula is helpful for a lot of students, so I want to show how to use that in the next video.